I'm Dick Wardrop, Chairman and Chief Executive Officer of AK Steel. You are about to see some of the most awesome sights you will ever witness, the making of steel. It's hard to imagine what our lives would be like without this versatile material. And even though steel is part of our daily lives, it is easy to overlook the thousands of ways we depend on steel around the world, and even beyond our planet in space. From the time you wake until your day is done, steel is working to make your life safer, stronger, and better. Just think for a moment of how steel helps you every day. The steel that supports homes and schools and skyscrapers and bridges, roads and dams. The steel that forms such essential modern conveniences like washers, dryers, stoves and refrigerators. The steel that makes your car safe and dependable for years. The development of large-scale steel production nearly 150 years ago provided the single most important milestone in a worldwide industrial revolution. As we approach the 21st century, steel continues to revolutionize the way we live. From the bolts that secure rocket boosters to the space shuttle, to ultralight and strong automobile bodies, steel is what the future is made of. What other material brings all these benefits to our lives, and does so as the most recycled material in North America? More steel is recycled than aluminum, paper, plastic, and glass combined. Now you might think that a product that can do all these things would be quite expensive. Well, here's another surprise from this incredible material. In fact, a pound of steel costs less today than a pound of butter or potatoes. Today's steel industry, and AK Steel in particular, utilizes some of the most advanced computer-controlled equipment in the world to produce the highest quality products. So I hope you enjoy this brief glimpse at how we make this incredible material at AK Steel, and I think you will agree that it is a fascinating process.
On a journey from the dark reaches of the universe, a meteorite hurtles through space. Nearing the Earth, gravity pulls it through the atmosphere. The mass explodes under the strain, raining bits of rock and iron on the ground. Following the streaking flight, the heavenly metal is recovered. The strange material is fashioned into a primitive tool. Fantasy? Perhaps. Or does it explain, as many think, why in ancient languages the word steel means star metal? We do know that man has used heavenly and earthly iron for thousands of years. In a time and place unrecorded came the discovery that iron could be made better, stronger, and even more useful. A pinch of nickel, a dash of manganese, dislodge a bit of carbon. The alloy steel was discovered. The age of alchemy gave birth to the science of metallurgy. In 1856, a process for making steel on a grand scale was discovered, and a tremendous industrial revolution was born. 150 years later, the evolution of new and better steels continues to unfold at AK Steel. It all begins, as it has for centuries, by assembling the essential ingredients. In northern Minnesota, miners coax ore from the rocky veins of the Mesabi Range. Straight from the ground, this taconite is unsuited for AK Steel's productive blast furnaces. Pulverized and concentrated, the iron ore is fused back together as marble-sized pellets. Steel rails will guide the ore to its final destination at the base of AK Steel's blast furnaces. 600 miles away, under the hills of West Virginia, miners dispatch tons of coal to the surface. It travels by rail to AK Steel's plants, where it will become the primary fuel in the 4,000-degree inferno needed to reduce the ore to molten iron. Before the coal can begin the demanding task of smelting iron, it must be transformed into a more efficient form called coke. The process begins by loading a blend of coals into a series of tall, narrow ovens. The ovens are sealed from the air to prevent the coal from burning away in the 2,400-degree temperature. After baking for nearly a day, a 12-ton volcano of coke is pushed from the oven into an awaiting rail car. Reunited with oxygen, the coke ignites in a scorching dance. Like charcoal, the coke is now light, porous, and strong. A 9,000-gallon cold shower tempers the heated passion of the coke, sending a billowy plume of steam skyward. Completing the raw material list is limestone. Mined from quarries throughout the Midwest, this natural cleansing agent will collect the impurities released from the coke and ore. West Virginia coal, limestone from Kentucky, taconite from Minnesota, and a pinch of high-grade iron from South America. These earthly ingredients will ascend 20 stories to meet in the iron maker's colossal vat. Skip cars haul their carefully measured burden up the steep incline, delivering a steady supply of fuel and ore to the furnace. A pair of valves, called bells, allow the raw materials to enter the furnace without releasing the pressure of hot air and gases in the furnace. To our metallurgists, this giant structure is known as a countercurrent packed bed thermochemical pressure vessel, but simply the blast furnace is named for its most indispensable ingredient, a blast of air and gas hot enough to ignite the coke. Stoves heat the air to nearly 2,000 degrees. Turbo engines propel the hot air at nearly 200 miles per hour into the furnace through openings called twires. The porous coke allows the hot wind to penetrate the raw materials and heat the ore. Oxygen reacts chemically with the coke, creating a reducing atmosphere. This thermochemical process creates temperatures of more than 4,000 degrees. Under this intense inferno, the ore releases molten iron, which drips to the bottom of the furnace. Gases from the reaction are cleaned and recycled as fuel for the coke ovens and blast furnace stoves. The limestone traps impurities released from the burning coke and ore, becoming a slag which floats atop the heavier molten iron. The iron and slag flow almost continuously from two tap holes near the bottom of the furnace. A drill pierces the clay plug of the tap hole and bores into the heart of the furnace. A 2,700-degree river of molten iron is born from the belly of the furnace in a spectacular display of man's command of nature. Unleashed, the fiery tide follows its directed course beneath the watchful eyes of its creators. With respect for its fury, the quality of the metal is monitored and recorded. The limestone, having performed its cleansing job, rides out of the furnace atop the river of iron. Diverted to a cooling pit, it will be recycled, perhaps as the bed of a new highway or railroad. Born of brittle, brute strength, the iron is destined for refining school, where it will learn to be rolled, drawn, and stretched as steel. Bearing more than 200 tons each, torpedo cars, haul the molten iron to the basic oxygen furnace, where it will complete its transformation into steel. Poured into a ladle, the iron is treated and skimmed to remove slag containing sulfur, an impurity left over from the coke in the blast furnace. While the iron is being skimmed, scrap steel, recycled from elsewhere in the mill, is loaded into the furnace. Cleansed of sulfur, the molten iron is poured into the mouth of the furnace. In a pulpit 200 feet from the fiery metal, the furnace is rocked, stirred, and monitored with computer-assisted precision. High-purity oxygen is blown into the furnace at supersonic speed through a water-cooled lance. Like a giant cutting torch, the oxygen lance raises the temperature of the iron to nearly 3,000 degrees, burning off yet more impurities in the iron and melting the scrap. In some 20 minutes, the rage of the furnace subsides, having tamed the iron's brittle strength. Rid of excess carbon, phosphorus, and silicon, the metal has newfound power. Steel is born. Having harnessed the energy of the sun itself, AK Steel's metallurgical chefs keep sentry over their bubbling recipe. A sample from the molten bath is retrieved. In the shop's metallurgical lab, quality control technicians analyze and record the composition of the metal. Before it solidifies, final adjustments are made to the chemistry. A vacuum degasser removes additional carbon. This allows the steel to be drawn and shaped into such products as automotive parts. Special alloys, titanium, aluminum, and manganese, among others, add special qualities for hundreds of different uses. A lid insulates the molten brew during casting. Capable of lifting the weight of nearly 200 cars, the crane operator's delicate touch hoists the ladle 4 stories high. Atop the caster, a gate is opened at the bottom of the ladle. Liquid steel flows through a shroud into a trough called a tundish at a rate of 5 tons per minute. Nozzles in the bottom of the tundish direct the steel into water-cooled molds. As the steel flows into the molds, it begins to solidify. Still soft, the steel is gently directed by the curved radius of the caster to a horizontal position at the run-out table. From molten steel, slabs emerge, glowing from an internal temperature of nearly 2,000 degrees. Automatic torches embrace the slabs, burning through the steel, which is now 9 inches thick. A tag is attached to record the slab's identity as the steel is processed into the customer's order. Still about 1,200 degrees, the slabs are cool enough to load on rail cars for their journey to the hot strip mill. More than 30 feet long, each slab weighs nearly 90,000 pounds. With enough energy to heat a city, the slabs are bathed in a glowing furnace for 3 hours. Shielded from the 2,400-degree heat of the slab, an operator sends the monolith toward its destination more than half a mile away. The slab's glow and unmistakable footsteps down the roll line are familiar signs at the hot strip. In 6 minutes, this 40-ton behemoth will make the most awesome transformation in steelmaking, as more than 130,000 horsepower press it as thin as a computer disk. The bar is squeezed between the huge roughing mill rolls like so much clay. Blasts of water break away the thin crust of scale that formed on the slab during heating, sending up a rooster tail of spray. The hot steel yields to the relentless hydraulic pressure in the only manner it can. Halfway to its destination, its 9-inch girth has been trimmed to a mere 1.5 inches. The rest of its mass now trails along more than 100 feet behind its front edge. Linked by a host of computers and radios, operators at the hot strip monitor every facet of the process. Some of the most advanced technology in the world controls the 7 finishing stands of the hot strip mill. Only several feet apart, these massive rolls give the strip its final thickness and shape. As the steel passes through each stand, its thickness is reduced further. By the time the front edge of the strip clears the final stand, it may be traveling more than 25 miles per hour. A half-mile from its blistering hot start, a cold spray cools the steel as it speeds toward the coilers. These marvels of timing catch the speeding strip and wind it into a coil. From glowing slab to glistening strip. What was minutes ago a mere 30 feet long, this coil would now span a dozen football fields. But the journey for this AK steel is far from over. This hot-rolled coil now has the fundamental strengths of steel. To meet the sophisticated requirements of many AK steel customers, these green coils, as they are called, will be further processed at the cold strip mill. At the pickling complex, a mild bath of hydrochloric acid removes the oxide that formed during the steel's journey through the hot strip mill. Following a rinse and a dry, the steel is again wound into a coil and coated with an oil to prevent rust and prepare it for rolling on the cold mill. In its basic operation, the cold mill functions much like the hot strip mill, squeezing the steel with tremendous hydraulic force to reduce its thickness. But as the name implies, no heat is applied in the cold mill. This creates a smooth finish and increases the strength of the steel. Although the steel isn't heated, friction from 2,400 tons of pressure readily vaporizes the mill's coolant as the strip speeds from stand to stand at 60 miles per hour. The mill rolls, costing up to $70,000 each, are changed every few hours to ensure consistent quality. AK Steel's trained operators have made this the most productive cold mill in the world, producing some of the highest quality steel available. Coils are inspected for the slightest blemish and thoroughly tested for all quality characteristics. For some customers, cold-rolled steel meets their requirements exactly. Its thickness has been reduced from that of a computer disk to a credit card. The surface is smooth, and the steel has gained strength in the cold rolling process. For the most demanding uses, however, additional processing will give the steel its final characteristics. At the zinc grip line, cold-rolled steel is immersed in a bath of molten zinc. This hot dip galvanizing process wraps the steel in a pure zinc rust-resistant coating. Automakers and other customers depend on AK Steel's industry leadership in steel technology for superior coated steels. These advanced materials help automakers build cars with extended warranties against rust and corrosion. Aluminum-coated, cold-rolled steels enable the makers of automotive exhaust systems to build mufflers, tailpipes, and resonators which last the lifetime of the car, if not longer. Aluminized steel is ideal for making furnaces and other heat-resistant products. Culverts and other drainage products fabricated from this aluminum-coated steel offer decades of service. Built to meet the needs for better automotive steels, the electro-galvanizing line plates cold-rolled steel electrolytically. Using the steel itself as a conductor, coatings of pure zinc and a zinc-nickel combination adhere to the strip in a giant 2 million amp electrical circuit. Electro-galvanized steels are preferred for their uniform finish, providing strong, smooth fenders, hoods, and other automotive body parts. For nearly 100 years, AK Steel's Middletown Works has been home to some of the most innovative thought and dedicated steelmakers in the world. Along the way, a few of our neighbors have found our Midwestern hospitality quite to their liking as well. On the banks of the Ohio River in Ashland, Kentucky, AK Steel's metallurgical expertise and hospitality are equally evident. In the Bluegrass State, we even gave our blast furnace a personality by fondly naming her Amanda. The largest of her kind in the world when she was built, Amanda just seems to get better with age. Day and night, Amanda feeds a steady diet of molten iron to Ashland's steelmaking shop. And it's a good thing, too, because the continuous caster at Ashland has the healthiest appetite in the world for steel. Built to produce steel for pipe, this caster was actually mothballed a few years ago when the need for oil and gas pipe all but disappeared. Redesigned for slabs, the men and women of AK Steel breathed new life into the machine and never looked back. They've given new meaning to the term continuous casting by setting world records with regularity. In what resembles a chess move designed for giants, a new heat of steel is traded for the empty ladle. The tundish, still full of molten steel, continues to feed the caster during the ladle change. Each day, Ashland's bounty of slabs embarks on an open-air train headed for Middletown, where they will help to satisfy the hunger of the hot strip mill. On the return trip, Middletown will send coils to supply Ashland's hot-dip galvanizing and galvannealing line. Fed by the Middletown cold mill, Ashland's versatile coating line produces both galvanized and galvannealed steels, a process that alloys the zinc coating into the base metal for high-quality automotive steels. 400 miles down the Ohio River from Ashland, the most remarkable steel facility in the world is springing to life near Rockport, Indiana. AK Steel's Rockport Works will feature one of the widest, most powerful, and by far the most productive cold mill in the world. A massive 60,000 horsepower mill, it will utilize some of the most advanced quality control and mill design in the world. It will produce carbon and stainless steels, allowing AK to serve additional customers in the automotive and food and chemical processing markets. Rockport's hot dip line will use AK Steel's legendary coating technology to produce the widest product available for the most demanding automotive customer requirements. Innovative pickling, annealing, and tempering facilities will complete this state-of-the-art addition to AK Steel's world-class facilities. Rockport will join Middletown and Ashland Works in a leap into 21st century steelmaking. Meeting the needs of its discriminating customers, the employees of AK Steel blend a heritage of steelmaking artistry with technology on the frontier of tomorrow. Coaxed from its humble earthly origins and transformed to glistening metal, steel is the fabric of our future. For more than 85 years, this versatile metal has formed the foundation of modern life. Shaping the cars and trucks of tomorrow, steel is meeting the challenge for lighter, stronger, and more versatile components, completely recyclable, but designed to last. At home, steel provides comfort and convenience in virtually every room, even in the very walls that shelter us from nature's rage. So what does the future hold for this adaptable metal with a distinguished past? At AK Steel, there is plenty of evidence to suggest the brightest days for steel have yet to be seen. Nearly 6,000 dedicated men and women have their hands and their minds on the most productive equipment in the world. For all its fiery origin and brute strength, steelmaking is a venture of the mind. And every day, those minds gaze into this metal's soul and ask silently, what if?
We're very pleased with the formability results we got on this fender.
And this is using Inland's Bay Hardenable steels?
This is our two-side EG Bay Hardenable off the continuous anneal line.
You know, no, if we look at this data, most of this material safely meets the core loss guarantee.
Let me just discuss with you the benefits that we see. The IN-spec product has many attributes.
Now, we've looked at heat-treated cranks in order to get the strength up, but the microalloy might be an approach, more uniform and easier to machine.
I think microalloy is definitely a candidate for this.
Bob, we've been able to identify that we have the capacity available through not only the RHOB, but the normalizer as well.
1000X, okay.
1000X is fine.
We're the experts on carbon and steel making, so they're looking for us to bring this together.
This part is very similar to some of the designs that are going to be manufactured 3 years from now. This whole quantity squared divided by the stiffness factor.
Inland's been market-driven for years now. And today our intent is to find relationships, partnerships with our customers so we can satisfy their needs, in fact, exceed their needs. And we'll do it through technology and our people. By working well in advance of that customer's production, we can anticipate their future needs and satisfy those needs with steel, with Inland Steel.
Steel from Inland. The process of manufacturing that steel, fulfilling the customer's needs, begins right here in America's industrial heartland, East Chicago, Indiana. At Inland's Indiana Harbor Works, its one steel-making plant. Since the Indiana Harbor Works opened in 1902, the plant has grown from 50 acres to more than 1,900 acres, producing more than 6 million tons of steel a year. But the plant's dramatic growth hasn't been in size alone. Steel making and steel makers have gone high-tech in every phase of the steel-making process. Extensive research and development, from the latest in computer-aided design and testing to advanced computer-automated process control.
Making iron, the first step in producing steel, used to be a relatively simple process of mining ore, coal, and limestone, and then smelting the mixture at extremely high temperatures into molten iron.
Today's specialty steel products demand a critical level of purity, only achievable through advanced materials technology. Technology to efficiently mine abundant low-grade ore, crush it, magnetically separate the iron-bearing particles, form the iron into pellets, and bake them hard. The end result? Iron ore that's actually purer than the old natural ores. Inland's technology goes one step further, baking limestone, a purifying agent called a flux, into the ore, producing fluxed pellets. The raw materials move to Inland's Indiana Harbor Works in special rail cars and giant ore vessels. These ships, which carry up to 60,000 tons of pellets in a single trip, are self-unloaders, capable of discharging their cargoes quickly and continuously. While the fluxed pellets arrive at Inland ready to use, coal, the indispensable fuel necessary for iron making, must be further refined and purified into coke before it will burn hot enough to make iron. Coking eliminates unwanted tar and gases by heat refining the coal in long vertical batteries of coking ovens. The coal is first charged into the individual ovens. After baking, the finished coke is pushed from the oven into a quench car and water-cooled. The coke then moves by conveyor to the blast furnace, where steel making begins. Among Inland's 9 blast furnaces is the largest and most advanced iron maker in the Western Hemisphere. Towering more than 300 feet high, this single blast furnace can produce more than 9,500 tons of pure molten iron a day, more than the combined output of 5 smaller furnaces.
To make quality steel, you have to make quality iron, and we make sure that's what comes out of this furnace.
Computers monitor every stage of the process, from the precise quantity of raw materials charged into the furnace to the exact chemistry and temperature of the hot metal. In one continuous process, the coke and fluxed pellets are conveyor charged into the furnace and blasted with superheated air and natural gas up to 3,000 degrees Fahrenheit. The intense heat melts the limestone in the fluxed pellets. The limestone combines with impurities in the iron to form slag, which then floats to the surface of the molten iron. Separated from the slag, the molten iron is tapped from the bottom of the furnace, running through troughs into specially lined pew ladle cars. Basic oxygen furnaces, or BOFs, can produce a heat or batch of more than 200 tons of prime steel in about 35 to 50 minutes. Here begins the intricate process of refining the iron into custom-tailored steel.
Making steel has been a tradition in my family. My father and my grandfather both worked for Inland, but they never dreamt it would be like this.
Basically, steel is iron, refined for added formability and strength. Approximately 90 tons of scrap, recycled steel, are charged into the furnace along with 200 tons of desulfurized iron. Alloys are added to give the steel special properties. A supersonic blast of pure oxygen is blown into the furnace, producing a powerful chemical reaction at temperatures above 3,000 degrees, refining the iron and scrap mixture into molten steel. Each individual heat is tailored to the customer's exact specifications. Some customers need ultra-pure, low-carbon steel for finer surface quality and formability. To achieve those standards, the steel is tapped from the BOF and further refined in a process called ladle metallurgy. Each of Inland's steelmaking shops has its own ladle met processing facilities. Powdered chemicals, alloys, and desulfurizing agents are added to the steel to achieve the customer's specific metallurgical and formability characteristics. To ensure maximum control over the steel's final chemistry, Inland uses vacuum degassing, a special ladle metallurgy process that siphons the molten steel into a degassing vessel where unwanted carbon and other impurities are removed. As the steel flows up one snorkel and back into the ladle through the second snorkel, alloys are added to the ultra-clean steel in an oxygen-free environment. Vacuum degassing produces clean, ultra-low carbon steels that customers can form into complex shapes previously unattainable. It also assures superior quality for electrical steels used in high-efficiency motors. Fine-tuned, the molten steel is ready for shaping in one of Inland's 4 continuous casters, which turn out slabs, blooms, and billets. Continuous casting enhances quality, conserves energy, and boosts productivity and yield.
The computers monitor the hundreds of variables in the process and quickly make any adjustments necessary to meet the spec.
The molten steel flows into the caster's water-cooled mold, where it begins to solidify and take shape. The strand of hot steel moves through a long automated series of horizontal and vertical rolls, which carefully shape it. Air and water sprays slowly cool the steel. The slabs, blooms, and billets are cut to length and transported for shaping and finishing at Inland's rolling mills. This 9-inch thick slab is about to be rolled into a 3,500-foot-long coil of hot-rolled sheet steel. The process begins by reheating the slab to 2,300 degrees for approximately 3 hours.
Today's customer surface quality standards will not tolerate even the smallest blemish. That's why we have these walking beam furnaces, so to give it the kid glove treatment, take the slab and put it on the line without as much as a scratch.
From here, a series of automated roughing and finishing stands, stretching more than half a mile long, roll the slab into sheet steel. Jets of water remove surface scale from the steel as it moves through the rolling stands. "11 wastewater recycling systems purify the water used in this and other processes at the plant. Sensing devices continuously transmit the slab's thickness, width, temperature, and squeezing force of the rolls to a computer, which instantaneously makes the adjustments necessary to ensure the coil's specs. In just 4 minutes, that 9-inch thick slab is rolled into a coil of sheet steel half a mile long and as thin as a dime. Hot-rolled sheet is the ideal material for products such as pipe and tubing, auto frames, rail cars, and construction and agricultural equipment. However, other products such as exposed automotive body parts, appliance cabinets, office furniture, and electric motors require a smoother surface finish, more precise thickness, and other mechanical properties. To achieve those qualities, the hot-rolled coil is cold-rolled at one of Inland's cold-rolling mills. The coil is first treated to a hot acid bath, called pickling, to remove any surface oxides. Then, without reheating, the coil is cold rolled in a tandem mill, where tremendous pressure reduces the steel's thickness. Since cold rolling hardens the steel, a heat treating process called annealing is used to restore formability. There are two ways to anneal steel. In batch annealing, the coils are slowly reheated for 5 days in large furnaces, where careful temperature control produces the precise combination of strength and formability. Using our advanced continuous annealing process, Inland reduces that annealing time to less than 10 minutes. The cold rolled steel enters the line and after cleaning, moves through a succession of heating and cooling processes that lock in the metal structure and strength.
This line simply isn't a high-speed replacement for batch annealing. We have the ability on this line through our very accurate furnace and quenching controls to be able to produce a product that has consistent physical properties throughout the entire length of the coil.
Once annealed, the steel is lightly cold rolled in a temper mill to improve its shape, surface, and mechanical properties. Inland's Indiana Harbor Works produces world-class cold-rolled sheet steel. But here in New Carlisle, Indiana, Inland and Nippon Steel Corporation have invested $500 million to build INTEC, the world's most advanced continuous rolling mill.
INTEC combines 5 previous steps into one: pickling, tandem rolling, annealing, temper rolling, and inspection. Our continuous automated line produces in less than 1 hour what traditionally took 12 days. INTEC produces the best cold-rolled sheet steel in the world.
Increasingly, today's customers are requiring cold-rolled sheet steel with the highest corrosion and heat resistance properties. To satisfy specific customer needs, Inland galvanizes or aluminizes the steel. Hot dip galvanizing passes the steel through a bath of molten zinc, while electrogalvanizing applies the zinc coating electrolytically. Both processes offer superior corrosion resistance. Aluminizing, coating the steel with aluminum, provides both heat and corrosion resistance. In addition to sheet steel, Inland produces a full line of plate, bar, and structural steel. Plates are flat-rolled products that are thicker than sheet for greater strength. Structural shapes include the wide flange and I-beams used in building and bridge construction. Today, as a result of continued investment in research, Inland leads the nation in the production of special quality bar products. The bar production process often begins in Inland's electric furnace steelmaking shop.
One of the big advantages of steel is that we can recycle it. In our 2 electric furnaces, we use a charge that's virtually 100% scrap.
Large amounts of carefully selected scrap are charged into the electric furnace. Giant electrodes are then lowered into the chamber, and in 2 hours, the intense heat produced by the arcing between the electrodes and scrap melts it into molten steel. Once the steel is tapped from the electric furnace, it moves to the ladle metallurgy station for fine-tuning. And then on to be continuously cast into semi-finished billets, which are reheated and rolled into a variety of bar products, including round, squares, and hexagons. Some bar users, however, require steel with metallurgical properties that only a basic oxygen furnace can impart. That steel is then rolled into billets, which are then reheated and rolled into finished bars.
It's impressive watching iron ore and coal and limestone become steel. And it's easy to get carried away with the technology and the machinery at work here. But it takes more than technology to make steel. It takes people. People who are committed to knowing the needs of our customers and doing whatever they have to do to satisfy those needs. It takes a company committed to hiring and nurturing the right people and providing them with the best technology in the world for their work.
The people of Inland Steel understand their role and commitment. Whether the final product is an automobile, an appliance, an electric motor, a piece of heavy equipment, construction materials, or whatever the product may be, it starts with them and high-quality steel. Steel from Inland.